All right. I guess it's working. Hi everyone. I'm Francesco, and you probably know me from podcastdatascienceathome.com. You can also take it from Apple Podcasts, Stitcher, Spotify, and many other channels there. I've been doing this for quite a few years now. I've been publishing something like 117 or 15 episodes so far. Pretty successful podcast, I must say. I'm very satisfied. And for those who don't know what the podcast about, it's basically about machine learning and artificial intelligence. I've been, I usually try to explain some of the, most recent findings in machine learning, and some other times also have a lot of fun demolishing the most hyped concepts in AI with due to the fact that AI is in fact a very hyped concept, and a lot of journalists are having fun describing things that are not really what they should be talking about. But anyway, I recently discovered this streaming channels, and they are amazing. I mean, I'm having a lot of fun, honestly, and also the fact that 2020 has been a different year that kind of pushed me going out with putting my face on a streaming or a video, and that's as we all know, this is going to be the new normal for a while. Now, I'm having a lot of fun streaming, but it's also having a lot of fun with a new programming language. Well, new for me because it's a 10-year-old programming language now, which is Rust. I've been speaking about this already in the episode about Rust and machine learning. It's a mini series that you can find on datascienceathome.com. But it's not about the podcast that I want to speak. It's not even about Rust, in fact, which is a great language. I'm probably gonna, dedicate an episode, a live streaming, I don't know how you guys call these things, to Rust. Which is an amazing language, and I'm probably gonna just summarize some of the best features of Rust, which is it's a low-level language. It allows you to touch the nitty-gritty of your operating system or hardware on which you run your operating system. It is not a garbage collected language, which is amazing because I come from C. Not really C++. I'm not really a fan of object-oriented programming, but in C, in fact, you have it's kind of the gold standard that in terms of performance. And when you want to benchmark new languages, that's where usually the comparison goes against. But anyway, it's an amazing language because, like C, it has very similar performance. Qualities. The code that is generated is quite optimized, though the compiler is not polished yet. But it's safe. It's a safe language, and so the problem of C is that you can touch the hardware and you can touch memory as much as you want, and the problem is that you can make a mess with your code, in fact, because you can have dangling pointers, double free, you can have invalid memory allocations or dereferencing invalid memory and so on and so forth, which usually means segmentation faults and so runtime errors, as well as, in the best case scenario, of course. Let me put some background music here. Usually it goes well. So I was saying about Rust is, about C, it lets you play with memory at a very low level, and this means that it gives the keys of the of your computer, of your hardware, which means that you have to know how to drive. If I can make a comparison with cars. The problem is that for very large projects, very large, pieces of software, it is, even the most expert programmer can mess around with pointers and double free and references and dereferencing, and so it can lead to very nasty bugs that have made history so far, unfortunately. Rust is a language that does not allow you to do that. So in fact, it is a new paradigm of programming that performs a lot of checks at compile time. This means that you can, even if you think maliciously, or you're just not as expert as you think you are, and you start creating these invalid memory allocations or deallocations or double free or stack-based buffer overflows and stuff like that, the compiler doesn't allow you to, and so it will stop. Your program will basically not compile, and this means that yes, you will spend much more time coding because you have to be clean when you code. But when your program runs at runtime, I would say that most of the time it goes, and I'm not saying it's magic. There's nothing magic behind that, but the compiler is just a piece of shit. Like. It stops you from doing nasty things, let me put it like that. So what is this about? Well, I've been playing with programming languages for basically my entire life. I come from C, and then I moved to artificial intelligence and machine learning. Now, of course, I don't want to give you the story of my life. I mean, I want to get down to coding, but Rust is a language that is growing. The community is extremely active. It's just an amazing community. I mean, I've been attending a few conferences, some even online, and I mean the work that these guys are putting together is amazing. And it's unfortunate that Mozilla has let some people go, but that will definitely not affect the future of Rust, which is just an amazing language in my opinion. Now, of course, out there are people who don't agree with me, and some of the folks are pro Go, pro C, against Rust, pro and against. It's like a football match all the time. All right, guys, I mean, peace. I like Rust. I code in Rust. I'm sorry if you don't like. Actually, it's not that I don't give a shit, but it's just like you don't choose a language because you like it or not. I mean, also that, but you choose a language for some properties that you would like to have in your software development workflow. Now, you like it, you don't, you sponsor Go, Golang, or whatever other language, fine with me. Now, when it comes to machine learning, I have to say that Rust is a systems programming language, and so when it comes to machine learning, we have seen Python being, the de facto standard in terms of, the programming language that is widely used and widely adopted by the community, and not only. When it's about neural networks and off-the-shelf algorithms in machine learning, we know that Python is the way to go. Oh, Python is the way to go. All right, well, whatever. Python is the way to go, really. The problem is that Python is quite shit. I've been learning Python for Actually, I've been using Python for the last many years, but if I could unlearn Python, I would be very happy. It's not a language that I like, honestly. It's something that I learned because of necessity. at the beginning it was fun, as in, you know, every new thing that you learn, it's always fun at the beginning, and then you start finding things that are really tedious and you don't really want to deal with. But you know, it's a quick and dirty way to show to build a prototype and show to the business, or whoever is paying for that development, something that actually works, does the job. It's not great, but it's good enough most of the time. Also for learning stuff, you know, data scientists usually are not supposed to be software developers, and so, you know, most of the time they deal with statistics, they deal with algorithms that are related to the statistical world, and definitely they know a little bit about how computers work. I've been fortunate enough to build my career around computer engineering, and then move to artificial intelligence and machine learning. So I already had that background, in terms of computer science, algorithm complexity, big O notation, all these things that are very, very important if you want to write code that actually performs. And most of the times I've found that my data science colleagues didn't have that. And so I've seen nested loops, nested tree 4 times, and then people asking why their code was not actually performing when, you know, things would have been done in a much linear way and much less complex solutions. But because the naive developer starts nesting things and on different variables and having this 4i, 4j, 4k, 4t, and then say, oh, what the fuck is happening to my code, and why it never ends. No shit, Sherlock. You nest 4 times. That's called n to the power of 4 complexity, which is extreme. Anyway, so Rust. Now, Rust and machine learning is 2 different worlds, right? That's the problem. And so the problem is that Rust is a very new language. There are not so many libraries when it comes to machine learning. There are some libraries that people are building. Libraries in Rust are called crates. Crates.io is the reference website for crates. And so if you need hashing functions, if you need arrays, if you need linear algebra libraries, that's the way, that's the place that you should be searching. But with this said, don't expect that you are going to find a very populated set of libraries when it comes to machine learning, as much as, for example, Python can offer. That's not the case yet. So I hope that this situation, I'm actually sure that this situation is going to change as we go, because Rust has been nominated the best programming language, or the one that developers love the most, or something like that. I don't know who puts this service out there, but I was reading that around. I don't actually believe that. It's kind of, what do you ask to developers? Like, do you love Rust? I mean, I'm not used to ask people and things if they love me or if I love them, so I just use them. But anyway, it's this number of crates is growing. There is a problem there as well. The number of crates that are out there is relatively large with respect to the functionality that they actually add. Many crates are just empty repositories, and some other crates are just not working the way they claim on crates.io. So I think there should be a bit of cleaning, and I hope that the Rust community is listening to this. I'll make sure that Twitter is going to be populated by these tweets that say, guys, please clean crates.io. It's quite annoying, especially when you are learning a new language. It's it's not nice when you have already the difficulty of the syntax and the fact that you are dealing with new stuff, and then in addition to that you have crates that do not work, or they are buggy, and so there should be a way to control these things or to flag somehow. So, but anyway, when it comes to machine learning, it's not a very interesting ecosystem just yet, with one exception, and that exception is called Lympha. Now, Lympha is a project that you can find on GitHub, of course. I will add some links, but anyway, it's on github.com/rust-ml/Lympha. Now, this is part of the RustML. ML stands for machine learning, of course, and that's a machine learning framework. Now, the RustML community it hasn't been so active so far, but I'm seeing that there is a bit more activity in the past few weeks. I don't know why. Honestly, I'm not asking that. I can sleep without knowing that, but it's a good thing. Now, the Rust machine learning framework has an objective, which is a very ambitious one, as the founder, author, Luca Palmieri, a good friend of mine. Hi, Luca. Thanks for this great initiative, and we have been speaking about this on the podcast as well, about Lympha. And as Luca mentioned, even in that episode, it's a very ambitious project, and of course, it can, this ambition can be satisfied only with the participation of the community and some other folks that are adding code, because that's the way a machine learning library can be written. The machine learning is a very large topic. You cannot expect to cover all that stuff in a new language in a matter of months, or make it complete enough for people to use these things. So it is required some effort from the community. So far in the Lympha repository, there are only 7 contributors. In fact, there are 8 contributors, and so I decided to contribute. So we're gonna be 9 soon. At least as soon as I commit and merge my local repository. But anyway, it's if you go on GitHub, you will see that there are different packages, or subfolders inside the Lympha. For example, Lympha clustering, kernel for kernel methods, linear logistic for linear regression, logistic regression implementations, reduction, I believe some sort of principal component analysis, dimensionality reduction, I believe so. I haven't opened that. SVM, support vector machines, and then there is one is very interesting, which is trees, which stands for decision trees, and I decided to contribute to the family of ensemble methods, which is, for example, random forest, XGBoost, and stuff like that. So I'm writing that part. There is a fork that is under my name at github.com/fgadaleta, FGADALETA, and I'm gonna commit soon. Probably it's already committed by the time that this episode is over. So what I want to do is, I'm learning Rust. I've been coding Rust for the past few months already. I'm not yet professionally proficient, but I'm getting there. It's taking some time. Rust has a relatively steep curve, learning curve. But yeah, I'm not scared at all. It's a very interesting language, and what I'm gonna do is contributing to Lympha as I learn Rust. Now, I usually have the tendency to write clean code, so I will spend a bit more time cleaning my code or writing the most performant solution that I can come up with. And so in that sense, I'm less proficient, for example, than Python, because I can get to those solutions in much shorter time, while with Rust it takes me a bit longer. But it's not that the code that I deliver with Rust is less of less quality, of lower quality. So yeah. Now, before in this first episode, I would like to go through the Lympha trees, the decision tree implementation, which I believe there is some room for improvement there. I've been reading that relatively, superficially. So I want to go through that code and explain and try to understand a bit of things with the author, and then move from there and basically implement a random forest solution. So random forest, as we all know, is a bunch of decision trees. It's called forest for a reason, haha. And so if the decision tree implementation works, the very next thing that we are going to do is how to implement a random forest based on the decision tree implementation. And then, of course, there will be hyperparameters to define on top of that, which is, for example, the number of trees, and some other things that are related to random forest, but more on that later, or probably in the next episode. In this one, I want to focus on the decision tree. So let's move to the code and let's see what happens there. So this is the so if you open Lympha trees, you will find the usual cargo, the cargo toml file, which is telling you what types of dependencies this crate is depending on. And this is another thing that I've seen Lookup being involved with, which is ND-array. It's an equivalent of NumPy for Python, much less mature, of course, but quite interesting project. And I've been reading some code there, some implementations of things that I know, that everybody knows in linear algebra. But it's always nice to see these things implemented in Rust. I consider it a very elegant language, honestly, and I think that as a learning exercise, if you're interested in learning Rust, take some algorithm that you know exactly how it works, even something simple, and just look if there is search if there is a Rust implementation, and just read it again. You will learn a lot of stuff. At least that's the way I've been studying Rust. After, of course, I've been reading the book and also the Rust programming language, which is a very nice book, and also Rust in Action. I think I read that with by McNamara. So the cargo, I keep diverging and from what I'm trying to say, and there's nobody stopping me there. But anyway, Lympha. So Lympha trees. This is the cargo of Lympha trees. This depends on it has a dependency which is Lympha clustering. I don't know when this is used. Let's find out. Well, all right. So let's see if you go under. Okay, so this is the algorithm. It's a quite long one. So I would start from hyperparameters because this is where you define some data structures that you are going to use. Now, when it comes to decision trees, there is. So how does a decision tree work? Well, let me explain. So algorithm first, code later. A decision tree is a tree with a root node, and every node can be a final node for this called a leaf, or it can be an internal node, and that node usually has two children, a left and a right child, right? Now, what happens in the node is that one feature of your data is selected, and usually this is done initially randomly. And this feature, for example, if you have a data frame of, let's say, housing, so you have like some demographic data, some characteristics of the house that you have in the data set, number of rooms or how many square meters, if there is a toilet, if there are two toilets, stuff like that. And then you have a price, right? The column price. Now, if you have to fit a decision tree, let's take a feature. So for example, number of rooms, right? Now, if you select one column, that's one feature. And so you will have one node that will tell, are the number of rooms less than 4 or greater than 4, or less than 2 or greater than 2, right? And so all the houses that have less than 2 rooms will fall in the left child, and all the houses that have more than 2 rooms will fall into the right child. And from there on, you will have another node with another feature, for example, the how many square meters, and again you will have a split less than or greater than a number, and all the houses less than that, smaller than that, will fall to the left, and the others fall to the right, and so on and so forth. And so what you are doing, in fact, is building a tree, right? Because you're adding nodes and children, and then you keep going down until you're no longer splitting, and there you go. So then you have for example, the prediction. In fact, you don't have a prediction, you have a classification of that particular sample. And if you follow the tree from the root until the leaves, in the leaves you will find usually, first of all, the number of records that have been classified at that leaf. So which means that if you follow the tree, you will find all the conditions of the features that sample that holds for that sample, and you will also find a class. So you will start grouping samples or rows in your data set by certain characteristics, which are the different features that you have been setting in the previous nodes, right? So that's a decision tree. Now, how do you split? So how do you split is, it's a long story. So I will squeeze it here. You split by entropy, or you split by Genie Gain. Now, Genie Gain there is a formula, I don't remember by heart, but it's in fact something related to entropy. And so it's the amount of uncertainty that you are removing after the split, right? So for example, if you have a split that classifies, at the right of which you classify 100% of the houses correctly, well, the gain that you have is amazing. It's the maximum gain. And so this means that the Genie is, will tell you exactly how, if that split is in fact, beneficial or not. So what you have to do is, in fact, once you select a feature, you will try a number of different values for these splits and recalculate the score all the time, and then you will choose the value with the best Genie score, which is the split that really splits the data in the most convenient way. So let's go back to the implementation, because it would be nice to see how these things are implemented in Rust. So the very first data structure that the author has thought about is the split quality, or the criterion is usually called, which can be Genie or entropy. And then there are the decision tree parameters. Now, as you can see, the decision tree parameters it's a struct with a number of fields. Now, here, stay with me because it's, of course, where do you have to go? Of course, you stay with me, Frankie, come on. So the decision tree params, so the author of this code has actually used some sort of pattern in Rust, which is so-called, it's called builder pattern. It's a practice. It's not mandatory to to write the code like that, but it's in fact convenient when you have a builder and that builds. This is the structure of a builder that can have some optional values, optional fields, and then you will implement a build method for this particular builder, and the build method will actually return a decision tree params, right? So it will return, it will check and eventually replace the optional values with something, some default value, and then it will return a decision tree params, in this case, type of variable. Now, the decision tree params is, so these are the parameters of the decision tree. So before I move to the implementation, I don't really agree with this code because I think there is a mistake in the way this decision tree params builder has been set up, and I will go to that later. Also because this is relatively dirty because it violates one important practice. I will show you later what I mean. All right, so let's go back to the parameters of the decision tree. So a decision tree is characterized by, for example, the number of classes. So, for example, let's assume we are dealing with a data set of houses, and these houses are labeled as expensive, cheap, very expensive, right? So 0, 1, 2, for example. So you have 3 classes. So n classes here is going to be 3. Now U64 is a bit too much, but okay, because it's an unsigned 64-bit value integer. It's huge. If you have so many classes, you probably have some continuous data. But anyway, I would have used something else. Use size, for example. But anyway, then we have the split quality. So the split quality it can be Genie or entropy, all right? Then we have the max depth. This is an optional value of U64. It's basically how deep you go, how deep you want the tree to be. Deep means that how many hops do you have from the root until the leaf. And then you have the mean sample split, so the minimum number of samples that you need for a split, and the minimum samples that you need to consider the terminal node, that is a leaf, right? And then the mean impurity, the minimal impurity decrease is to basically stop the learning somehow, because if you are, this will be an iterative algorithm that will explore all the possible values, all the possible features, and of course you need a stopping criterion for which you say if you're not improving more than this much, just stop. And that's exactly what the mean impurity decrease does. And then you have the decision tree params builder, which is exactly like the struct that we are going to build. That's why it doesn't really sound correct to me. I will implement this differently for the random forest, and it will be much shorter. But anyway, let's go. I'm checking there because there is a trait implementation. So let's implement the decision tree params builder. So this structure here, there are some utility methods like n classes that will set the number of classes to the self object. Split quality, it works the same. Max depth, it works the same. Mean substrate, these are all equal, so that's why we can just, you know, look at them and forget about them. And the build is something that returns a decision tree params. So as you can see here, the author is not doing anything, any control here. It just passes all these variables as they have been set directly. What I would have done is a check, because this is returning. So first of all right, that's why I think this is relatively wrong. I would have not put any decision tree any option value here. I would have put an actual value, right? So max depth has to be a U64. You like it or not. If you, as a user, you're not defining a max depth, then I will set some, you know, I don't know, 99 by default or something like that, or 42 by default. But I have to have a number there. And so I would have put a U64 here, right? And then an option here. That's an optional value. But then in the build, I would have checked. I would have made a check. So pretty much here in the build, I would have said, all right, since you gave me a max depth, which is an optional, I would unwrap that into something and see what is in there. And if there is nothing, set self max depth at a default value, and then pack all that stuff into a decision tree params function, right? But the thing is that is delegating the build to the decision tree params build. So before the author calls me and tells me how much full of shit I am, let me go and check this build, the delegated build, right? So let's check. In decision tree params, all right, so we have, oh yeah, so he wrote this, nice. So this is exactly the thing that I was mentioning before. But I have to be honest, the author has been smart enough to write this as a statement, you know, as a comment, but actually is a very wise guy. So he says, violates the convention that new should return a value of type self, which is very true. So the thing is that we are implementing a trait for decision tree params, and then we are returning, when we call the new, we're returning something else. So we're returning decision tree params builder. Now the compiler will allow you to do that because that's legit. No problem at all. But it's not nice, I must say. All right, so there is a convention that says if you are implementing a new method for a particular struct, just return fucking self, right? You know, that's the way you should do things. So if you return something else, fine with me, compiler says, but if you are a purist, not nice. So I will fix this. I will actually remove completely the build method here, and build actually nothing, just return decision tree params with the actual values that you have been checking in this build, right? That's what I would do. Okay. So let's see what he does. There is a new method here, and he passes only a number of classes, which is indeed the only thing that you need to build a decision tree. And then, of course, you can pass some default values like Genie by default. I think scikit-learn does that as well. They set Genie as a default split criterion. Max depth is none. Which probably means that you're gonna iterate until Lympha until mean samples and mean impurity decrease will tell you to stop. Mean sample split at 2 and mean sample split at 1. So we can have a leaf even with one element, and the minimum number of samples that you need to split is 2, which makes perfect sense. And then the impurity decrease has to be at least 0.00001. And then we have the build finally that receives all these arguments here and just returns a decision tree params. So this is a returning self, you see? This is okay. So when we call build, we actually return a decision tree params with these values, right? So that's it. So this is the first file. It's called hyperparameters decision tree, hyperparameters.rust. We move now to the algorithm. So the algorithm is a relatively, it's not that long, it's 400 lines of code. So let's see what are the data structures that the author has decided to build on top. So the first is row mask. I've seen this a number of times as well for performance reasons in Apache Arrow implementation, where they use bitmaps. Bitmaps are extremely efficient. These are the type of things that probably data scientists struggle with. And so a bitmap is a way to keep track of things in logarithmic complexity in terms of space, for example. So if you have n elements to keep track on whatever, for example, all the elements that are greater than a certain value, you can have a bitmap where every bit represents one element, and if that bit is, that bit is going to be Boolean for sure, and so that bit will represent if the ith element, the ith bit will represent if the ith element is greater or smaller than a certain value, right? So you can have a bitmap for every condition, and you will use bits instead of elements. So the element can be as big as you want, but the bit is just one bit. So, it's very efficient. So these are tricks that people use for speeding up things. And as well, in this algorithm, the author decided wisely to use a mask, which is a vector of bool. That's the row mask. We'll see where does he use this thing. It's getting dark in this room, and the background of my green screen is getting quite visible. Sorry about that, guys, but let me see if I can put some light. Oh, that's even worse. But anyway, I have to tighten or iron this screen. Next video is gonna be better. It's only the first, and there is always room for improvement in everything I do. Okay, so row mask. Now we implement row mask and we say, all right, so we return, so there is a method, all this gives me the number of samples and basically initializes the row mask with a vector of true, as many true as n samples, right? And so basically that's giving us the mask of all the elements where the vector of the bitmap, let's say, is all flipped with true, with ones, n samples time. All right, so we go down to sorted index. So this is interesting. He's using the sorted index to pre-sort elements in a column. So what he does here, it takes an array base. So this is a type that identifies the the data you're trying to fit to the decision tree. So that's a matrix, in fact. So if you are in front of the same data set that I told you, like the housing data set, it's gonna be, let's say, 1,000,000 rows, 1 row per house, and I don't know, 5, 6 columns. I said demographics, number of rooms, number of bathrooms, price, and the label. 6 columns, right? So 6 columns. These are the features. Now, what he does in this function here is saying, okay, give me the feature index, which is a number between 0 and 5, and give me the x, which is the data, and then I will slice a column, right? So I take the x at the feature index and I convert that to a vector. So I will basically take a vector, which is a sliced column. It's the vector of elements of the column at feature index. Okay? And then I sort them. This is very nice. This is very nice, as an Italian like myself would say. Very nice. And it's sorting. So this is a pattern. I've seen this a number of times. If you don't know Rust, it's gonna be a bit harsh. As you get familiar with Rust, this line 30, you're gonna get very familiar to these things. Let me put it up. It's so elegant. So it basically makes comparison with pairs of elements in the same column, and it applies an ordering, and basically this returns it sorts the column, and it keeps the indexes. So if we it takes the A and B and applies A.1 partial compare B.1. So A.0 are the indexes, A.0 and B.0, and A.1 and the B.1 are the actual values. So it makes comparison on the values and keeps the index, which is this first part here, the U size. So every A variable is a tuple, a reference to a tuple with the U size F64, which is the index and the actual element. And what it does is comparing the elements and keeping the index, so that I can have a list of indexes or indices, plural, of the pre-sorted values. So this is something that you can do in pandas as well, of course. When you want to sort an array and you want to return the indexes of the sorted elements, not the actual elements, but the indexes, it's much, much faster, because regardless of the type of the element, the indexes will always be that type, U size, right? And so that's also a very optimized way of sorting things. So it returns this, it sorts and returns the indexes into a sorted index structure. Okay, so this stuff is gonna be useful later when it splits, probably. Let's search. Let's find out. Okay, let's go down. Now here is the tree node. So this is the node of the tree, the decision tree. Remember, we start from a root node. In each node we have to decide what's the feature that we're going to split in that node. Of course, we need the split value, and then if we split, there will be a left child and a right child. Wisely enough, these are optional, because you might have a node that is a final node, a leaf node, and you don't have any children. Oh, there is a leaf node bool here. that will actually tell you if that node is terminal or not. And the prediction is the, I guess it's the label of all the elements that fall in that node. This is a very interesting construct. Box means that you are allocating on the heap. For those who know what the heap is, it's not the stack. No shit. So it makes an allocation on memory, in memory, and puts a tree node in that, which is this struct. So basically what you are implementing here is you have a node, you allocate memory for that node. If that node has left child, right child, there will be pointers to another node, and so on and so forth. So if you start from the root node, in fact, you can walk the tree down to the leaves. Now you will have to choose a strategy to walk that tree, and here we go into the realm of breadth first, depth first, but that's a different story. But basically, the only thing you need is the pointer to the root node, and then just walk down to the leaves. And I guess this is gonna be blowing. Oh, not that much. Oh, wait a minute. Boom. Yeah, it's gonna be huge. All right. So this is the fitting. This is the horsepower of decision trees. I will not go through the whole code because actually it's not that long. It's okay. All right, no problem. So let's see what happens at the node level, right? At the node level, we will create a fit function that basically takes x and y. X and y are training set, and y are the labels, right? Then you take the mask. At the beginning, they're going to be all the elements, and then you take the hyperparameters of the decision tree. You know how many, we said them before. Then we have the sorted indices of that particular of that particular feature that is specific to this tree node, and it's specified in the hyperparameters. Okay. And then we have the depth. So what's the depth that this node is at? Because otherwise we cannot stop. If we set some limit on the depth of the tree, when I create a new node, every time I create a new node, I will increase that depth. And so if I have a criterion that makes me stop if I reach a certain depth, that's how I keep track of things. So initially a node is not a leaf, right? And what we do here, we say leaf node is equal to leaf node, which is false, or the number of samples in the mask is lower than the minimum samples to split in the upper parameters. And that makes sense, right? If that happens, then leaf node stays false. Now, even if this is true, this guy here, well, if that is true, yeah, leaf node is gonna stay false. No way, it's gonna be true. It's an or. I tried to trick you. Bullshit. Yeah, okay, if it's true, the leaf node is gonna be true, right? Which is the stopping criterion. You didn't reach the minimum sample split. Okay, now hyperparameters max depth, so the max depth, let's say 4, right? Now what do we do here? You say if depth is, so the current depth is greater than the maximum depth that I accept, I have to stop. and leaf node is going to be true as well. So here we are setting some conditions that can stop the program immediately. Well, the fitting function, in fact. Then we have some parent class frequency. Okay, the class frequency, I don't know what it does yet, but we can skip it for now. I want to find something that you guys might be interested in, which is, I think it's this. Yeah, find the best split block. Right, so now in sorted index, as you can remember, in sorted index there is the feature index, right? So we have been sorting each column independently from the other. So this means that we have the feature index, right? And so we loop sorted indices dot iter dot enumerate, and we take the feature index and the sorted index, right? So this is like we take the index of something that is looping and the something. It's a tuple. So for each feature, which means for each column in our case, we say, okay, take the, I got it. So take the parent class frequency. This is probably the common class, right? The common class is like, I don't split, I don't select any feature, I don't fit any decision tree. What's the common class, right? Like it's like the baseline. So we do that, we clone that, and that's going to be the left class frequency, and the right class frequency is going to be for each class a vector of 0. So they all into the left class frequency at the beginning. And now we say so here, what does it do? Oh, wow. Okay. I know what it's doing. So he has been sorting the elements of that column before, because he called sorted index. Well, in fact, he passes sorted indices in the arguments here, right? So the caller of this fit has been doing that before. Okay. We will check that later. Now, this particular column, because every node is focusing on one column, right? So for this particular column, we have sorted elements, right? And now what we do, we pretty much count how many of these elements would go in the left class frequency and how many would in the right class frequency. Okay? So it basically takes the labels y at the pre-sorted indexes, and it moves them from the left class to the right class. So it decreases the number of elements in the left class, and it increases the number of elements in the right class. And then it counts and says if the number of elements, iter sum, yes, if the number of elements in the left class are less than the minimum number of samples per split, or the number of elements in the right class are less than, okay, so there is not a sufficient number of elements in any of the two classes that is sufficient for a split, well, then continue. Continue means go to the next feature, right? Because it's looping on I, and I is driving this guy here. So it says move to the next feature because there is not a sufficient number of samples to make the split. Then we take the split quality is Genie, default, and of course if the split quality is Genie, we make a match and we say you calculate the Genie impurity left and right. Okay. Right, so this is because it's calculating the Genie impurity. So to choose the best split, we need to measure the Genie before and after the split. And then we need to calculate the Genie gain, which is the Genie before minus the Genie after the split. And we have to maximize that, right? So that's why it's calculating the Genie impurity after the split on left and right class. Okay, let's keep entropy for now. Now, what is he doing here? Oh, nice. Is weighting the what the fuck is he doing there? Hang on. Oh, yes. So we are putting these two numbers in left score, right score. That's the Genie after the split on the left and the right side. And we can calculate that because we have the frequency on the left and on the right. Now, these are called left score and right score. Now, left score and right score have to be weighted with respect to what? To the number of elements in the left side and number of elements in the right side. And so that's exactly what's happening here. We take the weight is here, so we calculate basically the ratio, right, of how many elements in the left class divided by the total number of elements, and how many elements in the right class divided by the total number of elements. Wow, sorry guys, I was too down. Okay, I will repeat here. Okay. So it's we calculate, I repeat just the last minute. We calculate the Genie impurity on the left and right class frequency. Okay. Then we put these numbers, this is the Genie impurity calculated here and here. We put it in left score and right score. Now this is the Genie after the split, right? We need to calculate the Genie impurity before the split. And where is that? It's gonna be oh, it's here. Oh, it's outside of the block. Okay. Okay, that's fine. Yeah. I would have calculated that before. But anyway. It's the same. It's the same. So okay. Let me see where we are. There we are. So we calculate, all right, we calculate the rate So how many elements are in the left side of the split with respect to the total number of elements, and how many are in the right side with respect to the total number of elements. So this is the ratio, right? Or as we call left weight and right weight. And then we weight the left score by the number of elements in the left, the rate of elements in the left part plus the right score times the number of elements in the right side. And this is the overall score. This is the weighted sum, in fact. Weighted sum of left score, right score. Fine. Now, if best score is none, or if score is less than best score, what happens? Well, we save the feature index into the best feature index so far, the split value into the best split value so far, and the score to the best score so far, right? And if best score is none, this is true, then leaf node is gonna be true. Now we take best score and we kind of unwrap it, because in case we are using a Genie impurity, that's the Genie impurity before the split on the parent class frequency, right? Because now we have to take the parent score and we have to subtract the best score, which is the Genie impurity after the split. And if the difference between these two guys is less than the mean impurity decrease, then we stop, right? So this is when we are no longer improving. So if at this point we say, okay, if leaf node is true, we have been probing leaf node a number of times so far, remember. And if at this point it's true, well, that's it. Return tree node, in which you say leaf node is true, and this is what I found so far. Otherwise, if leaf node is still not true, it means that I'm still working, I'm still looping, I'm still finding the best feature and the best split, right? So then I continue my algorithm and I say, okay, let's take the best feature index, the best split value, and here we basically, that's cool. So this is where the performance is kicking in now, because we take the left mask here and the right mask. Okay, so these are in fact the positions in the bitmap. Oh, sorry, I touched the microphones so hard. So we take the bitmap, all right, of the elements in the left and the elements in the right. And now I say so for each row, so for each ith element in my data set, if mask of I is true, then I check that if I take the data set and I take the ith row and the best feature index, which is the column. So if a value is less than the best split value, I take that element and I move it to the left side of the split. So basically here we are applying what I said before about once you decide your split, what you have to do is going through all your elements in the data set For example, the split is about the number of room less than 2 or higher than 2 or greater than 2. This is exactly what's happening here. So you go through each element and then you say, well, if for this particular element xi, best feature index is number of room, is less than 2, the best split value, well then that element is gonna belong to the left side of the split, and which means that left mask I is equal true, so the ith element of the left mask is true, and the number of samples belonging to the left side of the split is plus equal 1, is incremented by 1. Otherwise I do that on the right side. At that point, I have two masks, the left mask and the right mask. Now, this is extremely important and really applause to the author. This is amazing because this is a way to keep track of elements without actually the elements, without the actual elements, but just with the bits, all right, where these elements are. So instead of moving things, I just reference and I say the ith element belongs to the left and the kth element belongs to the right. And so I only keep track of these indexes, not of the elements. The elements are there. I can only read from them. The only thing I move are the indexes. If I do too fast, you're gonna see the green screen. Anyway. All right, so what happens now? Okay, now for each element in the left side, I basically, oh, guys, wow, this is a recursion. Nice. So, well, is applying the fit. I will not explain this. You guys have to understand. This is basically applying the fit method on the left side of the split here and on the right side of the split. So it's a recursive function that will go down and reapply the fit on the new node. Genius. Let's take a minute to think about this. Maybe less than a minute. But let's pray together, guys. I love this. This is cool. All right. Maybe put some music. All right. Now, once this thing go down until the end of all the splits, what you're gonna do is returning this. And so tree node. So every time this fitting method will return a tree node. And by applying this tree node fit all the time, you're gonna return tree nodes. Okay, and basically apply these new tree nodes as children of the single node, of the current node, and so on and so forth. Now, we are almost done because, in fact, a decision tree is a bunch of nodes. And so that's exactly what we're going to implement here. A decision tree is a root node, a tree node, and the decision tree parameters, of course, but let me go up a bit. But that's it, right? So the only thing that you need to define a decision tree is the root node and the parameters. And then, as I said, you will follow the root node and you will go down to the left child, to the right child, and then to the children of the children until the leaves. Now the fit method, the fit function here for the decision tree structure, it's something that you give the data, X, and the labels, Y. And what it does, okay, initially it takes all the indexes, as many indexes as many rows. It's basically the ith element of that data set. It will sort the indices. Remember when I said the sorted indexes is passed by the caller of the fit? That's here. This is the caller. The decision tree fit is calling the tree node fit. And of course it's passing the sorted indices to the tree node fit. And that's it, because that's going to be the root node. And if there are other nodes, you can reach them from the root node by going into the left child and right child. So that's the only thing you need to return, a root node and hyperparameters. So this fit just returns self, which is this guy or girl. Noise. All right, so let's check predict. What predict is doing? Something very simple. We give an X and we want to know which label would that X be. As a return, it's an array as a vector, one-dimensional vector of U64. So if we are giving a matrix, for example, 1,000 by 6 columns, the features, well, in fact 5 because one is a label, we don't know. So 1,000 by 5, that's the X, the array base here. What you want back as a result is 1 by 1,000. So a vector of 1,000 elements where each element is a label of each element in the training set, in the X. And so what we do, we basically call make prediction on each row of X. And make prediction, I don't know what it does. Let's go check. It's here. So what it does, well, given the row, it says, okay, you also give me the node, the node that I have. It's gonna be the root node, right? Yes, it's gonna be the root node. It's basically the decision tree. And I say, if I give you a row, where in this tree will it fit? That's the prediction. So where you will follow all the features, all the single nodes, and check if where the particular row falls into as a leaf, because that's gonna be where the label is. And so what we do here, we say if node is a leaf node, well then just give me the node.prediction, because it's the end. Else if you take the node split value and you say if you take the row, the input row, and you say what is the value of the row that you're giving me at the column of this node. So let's say this is the node of number of rooms column, which is, I don't know, the third column. So what I'm doing there is like selecting the value of the third column. All the values of the third column of my input data. And then I check if that's less than the split value, then I'm a left element. And I have to run a prediction. I have to pass the ball to node.leftChild. Otherwise, I have to pass it to node right child and recall make prediction. So this is another recursive function. And once I'm done, I return, well, yeah, so we go back to the predict. So once I apply make prediction on each row, and I call into iter here, okay, and this is going to be an array, in fact, because array 1 from iter is telling me pack all these things, all these predictions that you are creating, you are performing, into an array into a one-dimensional array, which is the array 1 from iter part, line 239. That's pretty much it, guys. I mean, it's a nice algo. The next thing I'm gonna do is, of course, testing that this stuff is correct. Run some experiments with some known matrices and labels and see how it performs. I mean, first of all, check if the results that I get are correct. There could be a slight variation because in the way the random number generators are initialized. There is in scikit-learn there is a selection of features that is initially random, but actually the Genie criterion should converge to the same result, I believe. So I'm gonna run an experiment, see if this stuff works, and then the next episode is going to be my implementation of random forest. But before that, I want to let you know if this implementation is correct. Of course, I suggest you to contribute to Lympha. It's a very interesting project, and it's always good to rewrite things that you think you understand in a different language. If you like, of course, to write some Rust code, you're very welcome to contribute. We are looking for people like you that who can contribute and can extend the library or the crate as fast as possible, because ideally we should live in a Python-less world. Jokes apart, I like Python. It's a nice language. It's a quick and dirty language. Let me put it like this. It's not nice at all. I like strictly typed languages, but it does its job. I mean, I cannot deny the fact that Python is the de facto standard, but not for long. There are other languages that can make a difference out there, but that's not the topic of today. If you like to contribute to Rust, Rust is an amazing language. If you want to learn Rust, the best way to exercise is to re-implement things that you know. That's the only thing I've been doing so far. All right, folks, that's it for today, and I'll talk to you next time, and stay in touch. Thanks for following. Bye.